I will start working with chapter 6. Chapter 6 is a little bit long, and I'm not sure if I will do the whole chapter in one recording, or I will dissect. It depends. Okay. Now, chapter 6, we are going to talk about. Remember, we did cover in chapter 5, first law, Newton's first law, Newton's second law, Newton's third law, and now we will talk about the applications. Then we are going to have a physical situation where we might apply one of these laws, two, three, whatever, it depends. Now, I will say one of the situations, look here, it's looking maybe complicated a little bit, so many forces acting, but we will try to analyze it and find out how to calculate maybe one of these forces. Another addition here is we are going to include frictional forces, which we did not include when we were talking about, forces in chapter 5. We will also have some of the problems where we have strings and springs, and we will see if things they're going to change and how they're going to change, how we're going to include tensions. We are going to talk about one type of equilibrium, we call it translational equilibrium, and we will apply it and find out some of the forces that might be unknown. And then I will also have to go over some of the connected objects and how we are going to solve. And finally, we are going to go back to a little bit of kinematics, talking about circular motion, and then the dynamics also of circular motion. Okay, then all of these are going to be actually topics that we are going to introduce in this chapter. First, I will say we will not ignore frictional forces, of course, here, because frictional forces is one of the forces that it cannot be ignored. It's like it's always there. And maybe we want to increase I will say, we want to increase the frictional force by braking the car because the car is sliding, or we want to maybe have something that is working and we want to stop it. There are any other many things that, as I said, we cannot ignore friction forces because it cannot be eliminated. Now, friction, why we have frictional forces? This is because if we are going to examine the surfaces with, let's say, a very accurate, let's say, lens or something, you will find that they cannot be completely smooth. They have these bumps up and down, and they're gonna glitch, or they're gonna, I will say, come together, entangle together whenever there is an attempt to move the object. There are basically two types of friction. One of them is kinetic, and this is when we have the object is moving is in motion, then this is going to be kinetic friction. And also we have a static friction, which is going to be when the object is stationary or it is about to move. Now, the kinetic friction, it is the friction we have it when we have one of the object is sliding over the other. And I will say that here there is like a typo here, that I will say the kinetic, of course the static also, but because here we are talking about the kinetic frictional force depends on the normal force. And this is the formula, the equation that we are going to use, Fk. This is like these PowerPoints. I got them from Janet. Thank you very much. And she prefers to use FR, like force of friction. Like I used to use FK, but I might be switching between back and forth between this, because I noticed that now there is a point from that, like when I will say force of tension is going to be easier, and when I will say force of normal is going to be maybe easier, because sometimes you will be confused between the physical quantity and the unit. Okay, then I will say let's stick maybe with maybe FF friction. And I will say here mu k, it's a constant, it doesn't have any unit. It is called the coefficient of kinetic friction, and that constant depends on the two surfaces that they are gonna be in contact. The force of friction, it is always opposing to the motion, and this is I will say whenever the object is going to move, let's say to the right, we're going to say the force of friction to the left. Whenever we are going to to move upward, the frictional force downward, like it's always, I will say opposite to the motion. Now, one of the things that I want you to know, that normal force, it's not always mg. Okay, and maybe I did talk about this, not always. Okay, and this is here, it's gonna affect our calculation, because always we need to find what is really the force, the normal force first, F normal. Okay, we need to find what is the force of normal first, and then we will be able to calculate the I would say the FK. Now, frictional forces, also, we will say that the coefficient of friction depends on the properties of the two materials in contact. We have a surface that is a table in your textbook, which is gonna list for you some of the values. But remember, these values are not exact. Every time I want to introduce friction or talk about mu k or mu s, it should be, I should carry an experiment in the lab and find out these numbers. It is roughly independent of the sliding speed and area of contact, and we will say measured values here are really approximate, given the value will depend on things like if it is wet, dry, and how much were they sanded using like sandpaper or rubbed or whatever. Then it's like we will not be able to get exact values. But I want you to look at these, and just here, so always I bring to my student attention this one here, the synovial joints in humans. You can see it is 0.003 mu k, so that we move in easily. If this is gonna be like let's say 0.8, oh our life is gonna be very difficult. Also, the mu s, like if you look at it, is like this, maybe one of the smallest. Okay, also we need to talk about static friction, and when we talk about coefficients of static frictions, they are really higher than the kinetic friction. And always we say this kind of phrase, to keep the motion, it's much easier than to start the motion. Now, the static frictional force keeps an object from starting to move when a force is applied. The static friction always has a maximum value, and I want to here to talk to you about kind of a thought experiment that we have it here. And here I will assume that my force, okay, let me assume numbers. Let me assume this force here, it was 5 newtons. And here F2 was 10 newtons. And then here, F3 is, I don't want to give that a value now. Okay, just here, now, because here I'm talking about kinetic. I'm talking about mainly about a situation when the object did not move yet or it's about to move. Then here I will say F apply, here it is F applied, and here this is, I will say, force of friction. And I will say here in the first situation, my applied force was 0, then the force of friction was 0. Now, for the second value, which is the 5 newtons, I know that my object did not move, V equals 0, then the force of static friction is negative F1. And I will say here then is going to be 5. And then here it is 10, okay? And of course this is going to be 10 as well. The reason is the object did not move. It is like I can apply Newton's second law, Newton's first law, which is equilibrium. Okay, and there is maybe a maximum value that is really maybe like, let's say 15 here. And then after that, my object have started the motion. This one here, we call it Fs maximum. And only at this moment, I can say Fs is going to be mu s times the force of normal. All right. Then here, I will say Fs can be any number from 0 to mu s times Fn, which is here 0, 5, 10, okay, till it did reach 15. After that, this force here, which is needed to keep the motion, here I will talk about Fk, force of friction, and it is kinetic. Here I was talking about static friction. Okay, then the object now can keep the motion, and it needs less force to keep the motion, and the motion is going to be with, of course, acceleration. Now, here again, if this is related to what I was talking about, 0 less or equal than Fs, less than equal Fs maximum, and Fs maximum, it is mu s times the normal. Always you're going to have this question, am I talking about friction or static friction or kinetic friction? Okay, and always you need to know the physics so that you will be able to say and connect to life so that you will be able to say, shall I use static or shall I use kinetic? In this question here, a 10 kilogram box is being pulled horizontally across the floor with a force Fa, if applied. We're giving you here mu k as 0.3 and mu s as 0.4. And we want to determine what is the force of friction if Fa, the force applied, is 0, the force applied is 10, and the force applied is 20, like we are given different values. Now, of course, when I will say if applied is 0, the force of friction is going to be 0. Always we need to compare the values, the forces, with the Fs maximum, because at Fs maximum we will find that the object, where of course this is a mu s times normal, after that the object will move. Before that, the object is not in motion. Then I will first say, okay, I need, in order to calculate my Fs maximum, I need to first calculate the normal force, and then I can apply sigma Fy equals Fn minus mg equals 0. And in this case here, of course, the normal force Fn equals the weight of the object. Now, Fs maximum can be calculated as a mu s times times the normal force, and this is 39.2. Then here, any force that is going to be less than this force is going to be the force applied and the object is not in motion, or it is in an attempt, like, the threshold of the motion. And during that, we can say in all these cases that Fs equals F applied. Then if the force applied is 10, the force of static friction is 10. Because the object acceleration is 0, then you're going to say Fa minus Fs should equal 0, then they should be equal. If Fa 20, because it's less than 39.2, then Fs is 20. If Fa is 38, then Fs is going to be 38. Okay, when Fa, which is 40, greater, then I'm talking about kinetic friction, and then Fk will be calculated based on mu k times the normal, and it's going to be 29.4, and you can see it is less than the maximum, Fs maximum. Here, just to confirm your understanding for not having, I will say normal always equal to mg, we added a force, and we are going to find what is really the normal. In this example here, we have the same box, but instead being pulled by a horizontal force, it was pulled using a force that is making an angle 30 with the horizontal. Okay, and then we are trained to calculate what is really the acceleration of that, let's say, box. Of course, in all these solutions, we should have free body diagrams, okay? And the free body diagram is gonna be very similar to what we have in the picture here, but I like always to draw it without having the object so that it will be clearer. And I listed my quantities. I have the applied force, I have normal force, I have force of kinetic friction, I have the weight. I will apply Newton's second law for the vertical and for the horizontal. Here I need the vertical as well. The reason is we want to have the normal. Then you will apply for the horizontal, sigma fx equals max, and then I have fa cosine theta minus fk equals ma, and sigma fy equals 0, no acceleration, then fn plus fp sine theta minus mg equals 0, and from that I will be able to get my force, the normal force, as 78. I can calculate Fk, which is going to be mu k times Fn. Let's stick with the same notation here, Fn. And that from that I can get the value of friction. Now also I can apply, this is here along the x-axis where I have the acceleration. Fa cosine theta minus Fk should equal ma. And then I have the force applied times the cosine, minus the force of friction, and then I can get the acceleration as 1.1 meters per second squared. Okay, another example here. I can hold a box against a rough wall and prevent it from slipping down by pressing hard horizontally. How much force must you apply to prevent slipping? Okay, then here, again, free body diagram. I have force of friction should be upward, because if the object is gonna slip, is gonna move downward, then always you need to remember how, like, what is the expected motion, and then the friction is going to be in the opposite direction. Of course, I have the applied force and I have the normal force from the wall, and here is going to be horizontal because the object is it should be like sticking to the wall. Okay, I can apply Fx, sigma Fx equals 0, then the applied force should equal to the force of friction. And the F applied is going to be equal to the normal force. And also I know that from the y, that sigma Fy equals 0, then F the friction should equals the weight, and I will say I can maybe have a relation between the applied force and what is the mu s. Then this is the expression mg divided by mu s. Another one. On an icy day, you worry about parking your car in your driveway, which has an incline of 12 degrees. Your neighbor's driveway has an incline of 90, and the driveway across the street is at 6. The coefficient of static friction between tire rubber and the ice is 0.15. Which driveways will be safe to park in? What I will do is I will again do free body diagrams. I like when my problem has an inclination. I like to have my free body diagrams inclined as well. Now, of course, the expected motion is here. I like maybe to write this here. The expected motion and acceleration is going to be downward. Then the Fs max, it should be upward, and I have the normal force and I have mg. Now I will say sigma fx should, if fs maximum should equals mg sine theta, and for the fy, sigma fy should equal 0. Normal minus mg cosine theta is equals 0, then normal equals mg cosine. Now if s maximum is going to be mu s times the normal, then I can plug in the values, and from that I can find that mu s should equal tan the angle. Now my 0.15 mu s is going to give me an angle which is 8.53 degrees. Okay, and here I will leave it for you to tell which one is the one that is really safe to park, which driveway. We might have a quiz here. Okay. Also, one of the things that I want to talk, maybe I want to stop here because I don't want to make it very long, and then